All right, let's go ahead and get this going. Welcome everyone to the coffee break. Last one of 2025, if everybody can believe it. I hate saying it. It makes me even more nauseous than I am already, but that's where we're at. Excited about this one. We have recently brought on board along somebody who's highly revered in this industry. Um, Most people know him. If you don't, you soon will. His name is Mark Jelinski. He's a registered professional engineer, both mechanical and fire protection. Um, he's only been doing this for about 40 years, so I don't know if I trust him or not. But um, he was the chief mechanical engineer at RMH Group and has decided to take a different path here for a little bit and come help us out at Long. So, Mark, with that, why don't you go ahead and explain what it is we're going to do today?
All right. Well, thanks, Heavy. This was very exciting for me as well. So, what my role, first of all, I'm developing training programs both in-house, and we're going to be announcing in probably Q3 of 2026 Long University, which it will introduce HVAC fundamentals and application engineering to all y'all, the community that we serve. So, I'm also engineering assistants to our already very, engineering-based sales force here as well. What happens? For instance, I'll give you an example, and I'm going to use this as an example of the fundamentals that we'll be doing in Long University, as well as kind of engineering behind the scenes that we do. So let me just launch. Find my cursor. There we go. Just launch. Okay. So I'm going to get into psychrometrics, and really this is all about the fundamentals. So we're going to start at the beginning here. I'm going to really run through this. Sorry, guys, but that's the cool thing about this 15-minute thing. This is an abridged version, and please take your screenshots as you need to, or look at it when you can. The psych chart was developed to illustrate the properties of air over the range of what we do in HVAC. A given psych chart has a limited range and is unique for a given altitude. Make sure you're using the correct chart to begin with. Dry bulb temperature is what normal people call temperature. It's represented by the vertical lines on the chart, the x-axis. Wet bulb temperature is a measure of the amount of moisture in the air and is measured by the sloping lines on the psych chart. Relative humidity has nothing to do with the amount of cousins crammed in around the grandma's kitchen during a holiday meal. It's a measure of how much moisture the air can hold, right? And that is represented by the curving lines. And as you get warmer, the same temperature of air, it has the ability to hold more air, more water. That's why it feels dry, because it could hold more moisture than it currently is. At saturation, it's all the way to the right there. Humidity ratio is also known as absolute humidity, and it's in units of mass of water versus divided by mass of dry air. The true number of this is a very small number, 0.0 something. To make a more reasonable value, the unit grains is used on some psych charts and therefore in some of our calculations. That unit grains is 1/7,000th of a pound. Gotta love the IP system. This is represented by horizontal lines on the y-axis. Enthalpy is the energy level of this air-water mixture. It's in units of BTUs per pound and is represented by lines at essentially the same slope as wet bulb. Now that we know the notes, we can sing the song. HVAC processes can be represented on this chart. Humidification, dehumidification is represented by going up and down by vertical lines. Remember the humidity ratio, absolute humidity is on the y-axis, the right side of the chart here. The left-right, by going left-right on the chart, we represent a process of raising and lowering the temperature, heating and cooling. Both the vertical and the horizontal lines are crossing the sloping lines, which represent other properties, wet bulb, and most important, the enthalpy. So any one of these 2 points, A has more energy than B, C has more energy than D. In some of our real world applications, we do multiple. We do cooling and humidification. We change the temperature and we change the moisture level. Heating and humidification, we change the temperature up. We go from left to right, raising the temperature and raising the humidity level. Now, I'm showing a fairly practical cooling example. It starts off by just changing the temperature, what we call sensible cooling, going over to the left, but then the moisture starts to get wrung out of it. So it follows this curving line approaching the saturation line. What I'm showing here is a slope line for heating and humidification. In reality, we do that in 2 processes, probably. Most processes would be heating first and then humidifying. But it's represented that way. There's evaporative cooling. I'm sorry, I meant to, there we go, jump right into our problem here. So let's say that we've got a problem at hand. One of our sales engineers has a client who needs specific conditions being delivered. We're asked to provide whoops, I didn't want to do that. I wanted to do that. We're being asked to provide 4,000 CFM at 61 degrees dry bulb, 50 wet bulb. And the question is going to be, and we're told it's 100% outside air. So what value should we use for that outside air? ASHRAE weather climate data provides a couple different design values. A common value is the ASHRAE 4% cooling dry bulb with mean coincident wet bulb. That means that 99.6% of the hours of the year are lower than this temperature. That's why it seems like a good number to use as our cooling value, cooling design value. However, this is 100% outside air unit. So when I look at the other value, the ASHRAE 0.4% evaporation value, that's showing in our climate that even though the dry bulb temperature is lower than the dry bulb temperature of the typical cooling value used, the energy level is higher than that. So in order to come up, decide what the design conditions are going to be, the worst case design conditions, we got to use the higher energy level. All right, so we know we need to lower the humidity ratio below the desired supply air humidity ratio. And we were told, a desired leaving design condition is down here on the psych chart. So we got to cool down to at least that. And we know that it's going to be about saturated. So it's going to end up in this condition, 44-degree dry bulb, 43-degree wet bulb, which gets us below the desired relative humidity, the desired absolute humidity. This is probably going to be a draw through unit. By the way, another critical condition that we were given was that this needs to be, less expensive, a packaged unit. So I know that it's probably going to be a draw through unit because of that. That's going to add fan heat, and you can see my numbers here. It adds about 2 degrees of heat, and it slides over to the right there. But we're still too cold, aren't we? Airstream needs to be heated up. we can do this with a heating coil, but that's going to require a bunch of energy. It's actually about 27%. See, there's that delta H, the value and energy level between what's coming out of the unit and what we wanted. I mean, what's coming off the supply fan and what's coming out of what we want to come out of the unit. Is still requires an add of heat. And it's about 27% of what we just took out with the cooling coil. You know, besides being bad form, it's illegal according to the energy codes. So, you know, what kind of equipment could we propose to that? Have you got, I'm going to put you on the spot here. What would you use? Just packaged equipment to provide 100% outside. I'm sorry, I wanted to back up. I wanted to give a couple other options of what we could do here. A real, what we'd probably end up recommending, what I'd talk to have you about, we're not going to reheat this stuff, are we? No, we can propose to use a unit that comes with hot gas reheat. That's a very common packaged unit that, as part of the refrigeration cycle, takes the heat that we are already going to reject through the condenser to the exterior and to the ambient air, and has a separate coil in the supply airstream that takes some of that heat and reheats that air. First of all, that can be considered recovered energy, and therefore we're good with the energy police now. And further, it's a packaged equipment. We don't have to do anything fancy. Could we do something like a heat recovery wheel? Yeah, we can do things like that. But the desire here was for a simple packaged unit. And this is the topic of a coffee break we had some weeks ago that Matt presented, right, with DOAS units and right sizing DOAS units, and there's a great discussion about DOAS units and ratings and AHRI and moisture reducing levels. But the point is, that's what these things are built for. That's what we'd go back to the client with. And now, in order to, again, talking about could we do something different, just to get to the moisture level we desired, we pretty much had to brute force it with the cooling coil to get down below the humidity ratio that we needed. Well, okay, that's what you get with a packaged unit. We might be able to do something different if we were able to come up with some fancy stuff. How are we doing on time? I got another couple of minutes here. I wanted to get into, well, why did we do this? Why did we have to provide that dry air, first of all, and at a temperature of, 61 degrees? Couldn't we have just provided that 46-ish degree air coming off the fan? Well, yeah, maybe. But if we put 4,000 CFM of that air into the space, we would be overcooling the air. So I can kind of reverse engineer, and assuming that we needed about a 75 degree room temperature, I can see what the cooling load here is. Room sensible. And then, why did they make it so cold here? Well, perhaps to keep within below a 35%, here's 10, 20, 30, 35% relative humidity at 75 degrees. Okay, could have done that with 46 degree air, but the other thing is that in order to meet this delta H of cooling, we would have had to have had less supply air. Instead of 4,000 CFM, so that's about double the delta T there. We would have had to have half the supply CFM, but perhaps this is a lab or a process space that has a specific air change rate. Anyway, that's what we get with a client for, of course, right? But anyway, this is the engineering that we try to do, make sure that we understand what is being needed. And with that, I'm at time. So I will turn it back over to Heavy and let's see what we got for treats.
Great. Mark, that was awesome. And as you all can see, these topics that we want to get into Long University are extremely in depth. way too in depth for 15-minute little conversations like this, but we wanted to give you a little bit of a tickle. Not only for yourselves, if you need a refresher course like some of us, but also for, the young engineers out there who are just coming on board, any PEs out there with mechanical contracting firms. This class, this university that we're going to put on is a perfect training tool to get these young guys exposure to what it is and the meat and potatoes that we all do. So thank you, Mark. Can't wait to sit in on all these classes with you. Really appreciate it. Y'all stuck with us for a long time. Really appreciate it. And it's been several years we've been doing the coffee break. This year we decided to do something a little bit different. This is our last one of the year, so we have some pretty good prizes this year. We have 2 seats, first level, to the Denver Broncos game this Sunday. We have a Switch 2 from Nintendo, hot item. Now, just please note that the Switch 2 and the Sony TV are probably going to have to be ordered and or coordinated to be picked up. We don't have those in our hip pockets. But if you want to send me an email, I'm at atobin@long.com. If you do, the winner does decide to pick the tickets, and I can get those transferred to you. And let me see who today's winner is with my randomizer here. Enjoy the holidays. Merry Christmas. And we will see you all in 2026. Thanks for joining us. Bye.